Hello, so good morning everyone. I'm Serge Vaudenay. I have the pleasure to chair this session on authenticated encryption. In this session we will have three presentations, and the first one is a software merged between two papers about optimal authenticated encryption and making GCM great again. And this presentation will be done by Ashwin and Giwantak. And Ashwin is starting the presentation.
Yeah,
Please.
Thanks for the introduction. I will start with a brief motivation about the two works, and then contribution of my work, which is towards optimally secure deterministic authenticated encryption schemes. It's a joint work with Yulong, Abhijit, and Mridul. Let's start with an AEAD scheme, which is a symmetric key scheme. It has two algorithms, encryption and decryption. The encryption takes a key K, a nonce N, associated data A, and message M, and it returns a ciphertext tag pair CT. The decryption algorithm returns a valid message M prime if and only if the message M prime is a valid, if and only if the ciphertext C prime and tag T prime is a valid encryption of N prime, A prime, and M prime. So AEAD encrypts the message M and authenticates the metadata and message. It's a widely deployed primitive, and in most of the applications, we use a nonce, and the nonce is supposed to be unique in encryption schemes. On the other hand of the spectrum, we have deterministic AEAD, which is an AEAD without a nonce. Or you can just assume that the nonce is simply a metadata. It finds applications in database encryption and financial systems, mostly in tokenization. So if we have a deterministic AEAD, why do we need a nonce? So we need a nonce for security and efficiency. Because DAAD leaks equality whenever message and metadata is repeated. On the other hand, a nonce ensures fresh randomness per encryption query. And for this reason, a DAAD has to be two pass over the input, whereas a nonce-based scheme can be single pass. The catch, nonce reuse is strictly prohibited. For us cryptographers, this is simply a necessary condition that we cannot repeat the nonce. But in a real-world implementation, this necessity is often ignored, which you can see from all these examples that I found just by looking at the NIST RFC for block cipher modes. Juke showed for GCM that this reusing of nonces is actually leaking hash key. And then later, it's not surprising to see that Boak et al. Actually exploited this same idea to attack many HTTPS servers. In another direction, all these schemes, GCM, CCM, and OCB, are beyond the are limited to birthday-bound security. And if you instantiate them with AES-based, if you have an AES-based instantiation, then the security is up to 2 to the 64 queries. This might not be sufficient for many applications, including cloud-based systems. Another drawback is a limited generic multi-user security. Solution, standardize a bigger block cipher, and it seems like NIST is going for this. And it is an effective long-term solution, but in short term, replacing AES might not be that easy. Simple reason, because the setup time is going to be too much, because we have to develop the hardware support and a general cryptanalytic confidence in the new cipher. Another approach is to go for a BBB secure AEAD mode. So, for example, we can go for CHM or SCM or CVAR, which are all block cipher-based constructions. And they have certain nice features, but none of them is a one-stop solution for the two problems that I just mentioned. So, to solve the two problems, we propose to design a block cipher-based, efficient, misuse-resistant, BBB secure AEAD mode. Before I explain the designs, let's do a quick revision of the security notion. So we will be in the distinguishing game setup, where the adversary is trying to distinguish between two worlds, the real world and the ideal world. And the games will be defined by the ideal world functionality and the adversary's power. So for example, if sorry, it's not. Thanks. So, for example, for ideal world, if the ideal world is a uniform random function and the adversary is allowed to make chosen plain text queries, then we are in the PRF game. If the queries are now restricted to just uniform at random, then we are in the random IV-based PRF game. And for the misuse-resistant AE, the adversary is given access to a tuple of oracles, a uniform random function $, and the reject oracle bot, which basically outputs an error symbol for each decryption query. And of course, the adversary is not allowed to to relay back any encryption query output to a decryption query. A nice feature of DAADs is that it is MRAE secure naturally. So we'll go for a DAAD, and the best way to make it is using this synthetic IV mode or the SIV mode, which has two components, a PRF-F and a random IV-based PRF-G. The construction has nice, efficient features and a very clean composition bound that reduces the security to the security of F and G. So we have to develop a PRF component and an IV-based component, both with BBB security, and the IV size should be more than n bits. For the PRF component, we started with a construction from Eurocrypt 2020 that Nandi and myself designed with Cogliati. And this construction already has a very nice security bound. So it's almost optimal in the block size n, as long as the hash has certain good bounds. But the output size is limited to n bits. Well, it's not really a big issue, as we can simply duplicate the finalization, and we get n bit for additional 2 calls. Now, if we just instantiate the hash function with a good, efficient hash function like pmac plus like hash, then we get this construction that we call f star, and this is optimally secure in the total number of blocks. For the random IV-based PRF component, we have 2 options. For the first option, we started with Iwata's Cianc, which is again a very efficient construction and optimally secure for unique IVs, but it has 2 limitations. First, the IV is small, and second, it only achieves birthday-bound security in the random IV notion. We fix this by proposing giant star, which replaces the counter-based encoding with a lightweight and fast hash function and uses the random IV as a key. This inherits all the efficiency traits of Cianc, and we prove that it is secure if the hash is 2-wise independent. In particular, we prove that it is BBB secure for a large parameters of L, but still there is a factor of L here, and we want to drop it. So to drop it, we propose another option, and for this option, we went with we first looked into giant star for a fixed chunk. So for a fixed chunk of R blocks. And this construction, we call it star, and using the previous result, we were able to show that star is also optimally secure, and there is no parameter of length here. So all we have to do is to generate fresh 2n-bit randomness now, to instantiate each independent copy of star, and this gives us length-independent bound. So for this, G star must have length-independent bound as well. And for that, we allow G star to be relatively heavier than the previous construction. So in the paper, we have a 6 calls construction. But it's fine because it is called only once every R blocks. With this, the resulting construction, Snowflake, is proven to be optimally secure. So this brings me to our contributions, which are 2 AEAD modes, which are BBB secure and misuse resistant. The first one is DENC1, which is very efficient as visible from all these numbers. And the rate is almost optimal. So for DAAD, it is 0.5, so we are almost reaching that rate. But there is a factor of L because of this giant star as the random IV-based PRF. So we propose another construction, DENC2, which replaces giant star as the random IV-based PRF with a snowflake. And using that, we get a length-independent bound. Yeah. So with that, I'm done. And
thanks for the presentation, and thanks for also handling it over. And I will talk about making GCM great again toward full security and longer lenses. I'm the presenter Byung-hak Lee, and this is joint work with Woo-hyuk Chung, Sang-ah Hwang, Sang-kwang Kim, and Ju-young Lee. We had the same motivation but different goal. Recall that we require BBB secure AED with low nonce misusing risk. To achieve this goal, the natural way is to design a misuse-resistant AE. For example, we already have AES-GCM sieve, or of course, DNK1 and DNK2 are misuse-resistant. Those are best for security, but as Shane also mentioned, they have inherently two-path structure. So another way is to design a nonce-based AE with extended nonces. There is already DNDK GCM proposed by Shai Gueron, but the early version of DNDK GCM requires carefully generated nonces and block cipher with 20-bit key. So our goal is to construct a block cipher-based AE with full security, and we should give probable security under standard PRP assumption. And also, it should efficiently we should implement efficiently and to be comparable to GCM. Also, we want to support extended nonces or provide nonce misuse resistance, and also support arbitrary length message encryption. We share the same starting point, CENC. CENC is HCR type encryption mode with full security, but as Ashwin mentioned, it has limitation on its nonce length and counter length. So CENC-based AE construction still have nonce misusing risk and short length limitation. So we achieved same intermediate goal. We named it as enhanced CTR. Enhanced CTR is same as Giant Star, but it has structure of concrete hash implementation, instantiation. Enhanced CTR is almost fully secure variable output length PRF, but it requires random IV. It is enough for IV-based AE or SIV, but we also want nonce-based one. To achieve this goal, we proposed another building block, hashed and eCTR, or HTC in short. HTC is almost fully secure variable input length, variable output length PRF, or VIL-VOL PRF in short. But the key point of HTC is using universal hash then PRP style compression function. UH then PRP outputs, A and B in the figure, are not fully random, but we proved that it is enough for the eCTR input. By utilizing HTC and eCTR, we proposed enhanced variant of GCM and GCM sieve, eGCM and eGCM sieve. Let's see each of them in detail. eGCM is constructed by replacing CTR of GCM into HTC. Thanks to HTC's parameter, eGCM supports extended nonces and also support encrypting arbitrary length messages. It is also achieves BBB security for moderate message lengths, and if all message lengths are small enough, so we can set L as small constant, then it achieves full n-bit security. eGCM sieve is for misuse-resistant AE. It uses HTC as PRF and replace CTR into eCTR. It supports encrypting arbitrary length messages, and same as eGCM, it achieves BBB security for moderate message length. Of course, if all messages are small enough, it achieves full n-bit security. Here is the comparison from both papers. As you can see in the table, eGCM is the first nonce-based AE which achieves full n-bit security together with extended nonces. Also, eGCM sieve, DNK1, DNK2 are first full n-bit security in nonce misuse scenario, and note that DNK2 is the only one that achieves length independent security. Here's the benchmark of our constructions. You can see that eGCM is still comparable to GCM, and also eGCM sieve is still comparable to AES-GCM sieve. DNK1 and DNK2 are relatively slower, but remember that DNK2 achieves length-independent security. Here is the interesting comparison of two constructions from both papers. HTC uses arbitrary length nonsense, and it uses simpler compressing function, #PRP, but it has length-dependent security. On the other hand, Snowflake, right one, use random IVs, which is enough for SIV, but it cannot be used to construct non-space AE. But it has length-independent security. Length-independent security. However, the main bottleneck of Snowflake is G star, which is very heavy. So if we combine two ideas from two papers, we can make better construction. If G star in Snowflake is replaced by hashtag PRP in HCC, we get faster and construction that support nonce. So the result construction is variable input length, variable output length PRF with length-independent security. And it can be used to construct fully secure non-space AE and also deterministic AE. Here is the conclusion. The first paper was toward optimally secure deterministic AE, DNC1 and DNC2. Note that DNC2 is the only one which have length-independent security. And the second paper was making GCM great again. We proposed almost fully secure Bilbo PRF, and also from HCC we constructed EGCM and EGCM sieve. Here, EGCM is the only one with fully secure and supporting extended nonces. And we want to emphasize that our result can also be applied to other constructions. For example, we usually use hash, then counter the hash style accordion ciphers. Then we can simply replace the CTR in between two hashes into ECTR or Snowflake. Then we can get better construction. And also, as HCC and HCC plus Snowflake are secure PRF, secure and efficient PRF, we can use them as non-key derivation function. This is end of presentation, and thank you for attention.
Any question for the speakers? Yes.
Yes, thank you for a great talk. Can you just recap how many keys are used by each construction? Maybe you showed it, but there was a lot of information.
Yes, actually, in the paper we use a lot of keys. For example, HCC requires 2 hash keys and 1 intermediate block cipher key, and ECTR requires another block cipher key. So yes, we require 4. Moreover, we have another hash key. But actually, we can use the key derivation function.
Would it be possible to modify the constructions to use a single key without key derivation?
So we can also just use domain separation. So if you use domain separation, I think HTEC, I think we can make it 2 keys, because the hash function and the PRP layer, it can use the same key. And then the ECTR will use another key. So the two, for example, for SIV, the 2 components individually will need 2 keys. So in total, we still have 4 keys, but yeah.
But can you make it 1?
Any other question? Okay, so let's thank the speakers again. So next, we have efficient instances of Docker double-decker with AES and application to authenticated encryption by Krzysztof Dobronik, Christian Maturziewicz, Bart Menink, Alexander Tereschenko, and Krzysztof is almost ready to give the talk. It is falling. Okay.
No. Oh, now it's working. Now it's working. Thanks for the nice introduction and welcome to my presentation of some work I did together with Christian, Bart, and Alexander. And so the goal of this work was to look for instances or instantiations of the doc double-decker only using widely available building blocks AES and functions based on GHAS, while also trying to be as parallel as possible during each stage of the doc double-decker. And in addition, we also wanted to see if we can reach beyond birthday-bound security. So first, we have the notes and disclaimers. You can read it here or later online on the slides. And let's start with the overview. First, we review what the doc double-decker is. Then I will present the 3 instances that we have. I will give some design rationale, why we designed them as we did, and afterwards I give some practical implications of beyond birthday-bound security. So let's start with the doc double-decker. It's designed by Gunzig, Dahmen, and Manning. And as you can see here, it's essentially a 4-on-Feistel network, which has 2 different building blocks, 2 times the stream cipher, and in the middle of the cipher, and on the outside you have universal hash functions. This construction is what some people call a Twickel wide block cipher, or also accordion cipher mode. So you can think of it as a Twickel block cipher, but you can choose your block size. So basically on the left and right hand side you have your end-bit handles, and in the middle you have this thing that accordions and can be any length. What's nice about the doc double-decker is it's security bound, as you can see in this bound. So the total number of queries, the sum of queries to the constructions are recorded, but also the number of queries per tweak W used, which means that in the general case you get birthday-bound security of the doc double-decker, but the security can significantly increase when tweaks are not reused too often. So what were our goals and hurdles to overcome? As I've already mentioned on the title slide, so we wanted to build it on widely used components, AES and operations in binary extension fields. We wanted to make it as efficient as we can, which essentially means as parallel as we can. And we want to also have birthday-bound and beyond birthday-bound secure instances. The hurdles that we have to overcome were mainly AES. Since it's not a Twickel block cipher, it has this rather small 128-bit block size. And as a result, typical stream cipher modes that use AES only give birthday-bound security. So the first component that we use is the universal hash function, which is the same for all instantiations. It's just polyval. We just selected it because there is widespread hardware support for it already. So our instances really just differ in their BRF or stream cipher, if you will. So for our first instance, the birthday-bound secure DDD AES, we just use an XC-style Twickel block cipher. So essentially, we just encrypt a domain separator, which is the B, and the tweak W, which gives you S, and S is then always multiplied by 2. We have also designed a cipher which we call DDD AES Plus, which supports variable length tweaks as input. And yeah, we started the design 1.5 years ago before NIST gave out any call for requirements, or so we were kind of surprised that they wanted to see variable length tweaks. And for birthday-bound secure instances, having variable length tweaks is kind of easy to achieve. So you can either use a universal hash to essentially hash the tweak, or you can use, as we did here, you can essentially use a block cipher to essentially compress the tweak down, and then do, again, the multiplication with 2 to have your counter. The reason why we use a block cipher and not universal hash, we will see after the next slide. But before we come to that, we go to our beyond birthday bound secure instance, which is BBB DDD-AES. And for that, the BRF that we use is a thing we designed that's based on XORP, which is tweakable XORP. So it's just XORP extended to include the tweak. And again, we compute the value S by using a block cipher, but this time it takes the domain separator, the tweak, and also some counters. And yeah, as in XORP, you then essentially have the sum of two block cipher calls, where one part is for the most time constant. And for this construction, we aim for 2 to the power of 2 1/3 BRF security in the case that the tweaks are not reused too often. So let's have a look at the design rationale and take a look at the full picture of DDD-AES in the case we want to encrypt 512-bit blocks. Here you can see the different layers that can be computed in parallel, essentially, in different colors, red, green, orange, and blue. And then we have the tweak processing, essentially, that can be performed independent of the data input. And now on the right-hand side, we essentially have this scenario where we have different hardware accelerators, 2 of each type, so 2 for AES and 2 for the finite field multiplication, and we assume that they take roughly the same time. What you can see then now, if we assume that plaintext and tweak come at the same time, is that we can start with the AES engines processing of the tweak, while we start the processing of the data using the finite field multiplications. And once the finite field multiplications are done, or the universal hash is done, we can start with computing the first stream cipher and then the second ones. And for the second ones, we can operate them interleaved like in AES GCM to the second universal hash functions. And here from this picture, you can see why for DDD-AES Plus we decided to use the block cipher AES to process the tweak, is because we have empty space here where we can fit the tweak processing. And the longer the block size gets, the more empty space we have, and we can essentially process the tweak for free. You can see it. Or we have a better utilization of components. What's interesting is if we move to the beyond birthday bound secure instance, you can see that the core of the cipher stays the same. We just do essentially more tweak or more mask processing, so you will. And the nice thing is that everything is still nicely parallel, so essentially the critical path stays the same, so you essentially go through multiplication, then block cipher, multiplication again. And also with the beyond birthday bound secure instance, we can make use of the mask processing to fill the previously underutilized AES engines. And this has the effect that in this scenario, we just end 1 unit in time later than the non-beyond birthday bound secure instance. With tweakable block ciphers, you can also do authenticated encryption. And one way to do it is to just take the nonce and concatenate it with the associated data and put it into the tweak, and then encrypt the plaintext padded with zeros to the ciphertext. So in our context, we can do this with DDD-AES Plus. since we kind of have a variable tweak size, but if we have a fixed tweak, you have to think about something else to process associated data. And this can also be quite done in a simple manner. So essentially what you just have to do is to replace the zero padding that you had before with processing concatenation of nonce and associated data via universal hash. And the result is a quite nice, efficient authenticated encryption scheme that gives you security in nonce misuse scenarios and very good security in nonce respecting and even random nonce scenarios. Yes, that's what I've said. And some examples why having beyond birthday bound instances is nice. Essentially, as you can see here, if we compare memory encryption, AES XDS with beyond birthday bound secure instance, you can see that a single key is able to protect just much more of data. Also, if we would use it as authenticated encryption in TLS, having this beyond birthday security just means that you can encrypt more records. Plus, you have also the nice benefits like your nonce misuse resistance. So that brings me to the conclusion. Basically, we have introduced 3 schemes. They come with security reduction to AES, and we've also introduced this authenticated encryption mode for tweakable block ciphers where you have a fixed tweak size. So thanks for your attention.
Any question? Damien.
Thanks, Christoph, for a nice talk. Have you also studied a scenario where you only have one of each of the accelerators? So one AES, one multiplicator. Does it degrade gracefully?
Yes, I think so, yeah.
Okay, thanks.
So this is like a political question. So is it possible to believe that NIST has never yet tried to standardize probable secure symmetric encryption?
Yeah, I don't know.
Okay, any other question? Yes.
Why do you make the assumption that field multiplications and AES are like equally fast? And what happens if would you make different design choices if field multiplications were faster?
No, not really. So basically, yeah. So also, if you consider field multiplication faster than AES, for instance, for wider block encryptions, you will still have this gap here. So yeah. Just want to fill it.
Anything else? Okay, so let's thank the speaker again.
Thank you.
So the last talk of this session is entitled Committing Authenticated Encryption, Generic Transform with Hash Functions by Shan Chen and Vukasin Karadzic. And Vukasin is here.
Yeah. Hi, thanks for the introduction. So my name is Vukasin Karadzic, and in this joint work with Chan, we looked at how can we investigate, how can we build black box generic transforms that are committing a, let me start with the basics. So in AE primitive, we have 2 algorithms, which are the encryption algorithm that takes in the key, the nonce, the associated data, and the message, and outputs the ciphertext C. And we have the decryption algorithm that takes in the key, the nonce, associated data, and ciphertext, and outputs either the message M, if the decryption was successful, or the error symbol bot, if the decryption was not successful. And conventionally, there's two security notions that an AED is supposed to satisfy. The first one being the privacy one, which says if we have a secret and random key, whatever the adversary queries, the ciphertext should be indistinguishable from random bits. The other one is the authenticity, and there we have that for any forgery attempt by the adversary, the decryption algorithm will always return the error symbol bottom. In addition, we have one small additional restriction, which is that the adversary cannot repeat the nonce to the encryption algorithm. However, since 2017, there's been a couple of attacks that highlighted the need for a security notion that goes beyond the classical privacy and authenticity, and it is the committing security. And there's many definitions for committing security, and in our work we focus on the strongest one, which is the CMT notion. So it was introduced as CMT4 notion concurrently by Chan and Rogaway and Belar and Hong in 2022. And there's also a simpler equivalent notion that is called CMT3. And we call both CMT3 and CMT4 just CMT. Okay, and what does the notion say? So the adversary cannot output two tuples, key K, N, A, D, and M, and K prime, N prime, A, D prime, and M prime that are different, such that they encrypt to the same ciphertext. Then the previous work also showed that popular and deployed AES schemes like AES-GCM, Chacha-Poly, and others are not committing. There was also some dedicated modification proposed, like Belar and Hong proposed dedicated modification, like a very simple modification to AES-GCM to make it committing. And there's been a lot of work on generic transforms. So how can we use the generic transforms to achieve committing AES schemes? And in our work, we focus on generic transforms, since they're important to study both from the theoretical perspective as well as from practical point of view. We noticed that existing generic transforms have one of the following shortcomings. So first, they're either not committing to the entire encryption context, such is the case with the commit key by Albertini et al., which only satisfies a weaker notion of key committing. They involve non-standard primitives, such as the case with SIV, like the classical SIV, which was shown by Baumik et al. Last year, that in order for SIV to be CMT secure, you would need to use a key committing MAC. Then there are not a black box transform, such as the CTX by Chan and Rogaway, which uses the tag-based AE. So the AE does not output a single unified ciphertext, but it outputs a coarse ciphertext and the tag separately. And finally, they provide limited committing security, which is the case with Pact and Compact by Bhattacharjee, Baumik, and Dar, where the committing tag comes from the block cipher, so meaning the size of the committing tag is limited, and then the security is limited as well. And yeah, we set out to investigate how to achieve committing AE using black box generic transforms with standardized primitives. And we first needed to choose the building blocks. The first obvious one is the encryption, that is authenticated encryption schemes. And we looked at both privacy-only encryption schemes and AE schemes, because it allows us then, for some of our transforms, to have them work only with privacy-only encryption schemes. And the other building block, which you may conclude from the title, are the hash functions. So first, To achieve CMT secure AE, some idealized assumption like ideal cipher or random oracle model is currently unavoidable, at least for practical instantiations. And we opted out to use the hash functions and the random oracle model. Since they are widely deployed and non-primitive, they easily give us the committing property via the collision resistance property of the hash functions, and the CMT security can easily be increased by just taking the longer digest. We then took these two building blocks, tried to match them in different order, and get some secure composition, and this is what we got. So our first transform that we call hash then AE first takes in the key, the nonce, and AD, and hashes it, and outputs two blocks. The first block is used to rekey the underlying AE. The underlying AE takes in just the nonce and the message, so no AD input, and outputs the ciphertext C. And to come back to the hash output, the other output block is the committing tag T. And here I would like to highlight, although like the rekey is costly, our H then AE exhibits similar performance to the other generic transforms that have this internal rekey. Then the second transform is the AE and hash. Here the AE again takes in just the nonce and the message and outputs the ciphertext C, and the hash takes in the key, the nonce, and AD to output a committing tag T. And the main benefit of our AE and H is that it is fully parallelizable. Our third transform that we call encrypt then hash works only with a encryption scheme that is privacy secure, but of course it can also be AE, since every AE scheme is also privacy secure E. And here the E takes in the nonce and the message again, no AD, to produce a ciphertext C, and then the ciphertext is hashed together with a key, nonce, and the associated data to get the committing tag T. And exactly this is the possibility to change whether we want to use E or AE, what gives us this crypto agility. As for the security results, we show that our H then AE, A and H, and E then H are privacy, authenticity, and CMT secure. So we also implemented our transforms and comparable transforms in OpenSSL and WolfSSL. And we measure the performance of the transforms as the overhead over the performance costs of the baseline non-committing ASGCM. One thing that I want to note, so all transforms are implemented using only black box primitive implementations from the corresponding library. So we just use the API of the library. There's no crypto development here. And using just the API of the library is what your average practitioner would do in the real world. Since I don't have that much time, I'll highlight here. So our recommendation is use our AE and H if you aim for efficiency, and you can use the E and H if you have short messages and or only access to the privacy-only encryption scheme E. An additional side note, so our AE and H, which is fully parallelizable, so implementation here is sequential, meaning we take an AE from the library, we take the hash, we run the AE, after that we run the hash, and that is how we implemented it. And what I wanted to say, so dedicated implementation would perform even better. So what happens, so if one repeats the nonce for all of these transforms to the encryption and violates this restriction that a security definition imposes. Well, the transforms break down. They do not offer us any security anymore because the underlying AE will not offer us any security anymore. However, we can relax this restriction, and then we are talking about the stronger nonce misuse resistant AE or MRAE notion. And we have some solutions for that as well. The first transform that we give is the MRAE preserving transform that we call A then H. We call it preserving because we assume the underlying AE is already MRAE secure. And our design for AE then H is not new, so it is a black box generalization of the CTX transform, but the authors of CTX did not show the security for MRAE security. And as I'll show you later, there's also one additional practical benefit of our A then H being a black box transform over the CTX. And the security result for our A then H says the following. So if we have an MRAE secure AE and a collision resistant hash function H, our A then H is MRAE and CMT secure. The other transform that we presented is the CHASIV transform, where CHASIV stands for committing hash-based SIV. So SIV is there because this hashing of the message nonce and the associated data to get the tag and the IV for the encryption is exactly what happens in original SIV, although they use the MAC instead of a hash. Here, in addition to the encryption and hash function, we also do have a PRF. But this PRF in practice can be just instantiated with AES, so no new primitive implementation would be needed. Then again, we have encryption scheme E that can be only privacy secure encryption scheme, but also could also work to if it were an AE. And our CHASIV is the first generic transform that promotes plain AE to a committing MRAE secure scheme. In the security result for CHASIV is the following. So if we have privacy secure encryption scheme E, a collision resistant hash function H, and a secure PRF F, we know that CHASIV is MRAE and CMT secure. And similarly to the basic transform, we also implemented the encryption algorithm of our transforms and other comparable transforms that aim for MRAE security. So here now we have on the y-axis for the OpenSSL, we have the overhead over AES GCM SIV, which is the MRAE that we used in OpenSSL. And for WolfSSL, we calculate the performance as an overhead over AES SIV, since that is the only available MRAE in WolfSSL. And again, the note, so we are just using the API of the libraries, no crypto development. Out of the MRAE preserving transforms, we see that our A then H performs the best. And here is the point about A then H being a black box generalization of CTX. So the CTX decryption algorithm, because it is not a black box transform, would need 2 passes using OpenSSL's API, and would even be impossible in WolfSSL because the API does not allow to just decrypt the core ciphertext. Yes, and then going to our CHASIV. So very interestingly, in WolfSSL, CHASIV, yeah, that should be CHASIV beats the benchmark AES SIV for all tested message lengths. And in OpenSSL, the chassis beats the benchmark AS/GCM SIV for long messages. And the two can be explained with the fact, so first in WolfSSL, the AS/SIV has a really, really slow implementation, and then the chassis, which uses hardware-optimized E and hardware-optimized SHA-512, which we use as a hash function, they beat the AS/SIV. In OpenSSL, the AS/GCM SIV implementation is just partially optimized, so it's not fully optimized, and that's where this faster chassis comes from. And the takeaway for you from my talk would be, so we introduced the 3 basic committing AE secure transforms and 2 advanced committing MRE secure transforms. They are conceptually easy to grasp and implement using only standardized primitives. They turn out to be very efficient and implemented only with black box primitives from common cryptographic libraries. And finally, so our hope was and is this would lead to a faster adoption of a committing AAD. And please, contact us if this sounds interesting. There's a link to the ePrint paper, which has many more details. For example, we show all of our transforms also are CDY secure, which is a notion related to the commitment security. There's also a link to the core artifact that got the IACR results reproduced badge. So that would be all. Thank you for listening, and I'll be happy to take any questions.
Any question?
Thank you for the talk, very nice work. You didn't show us any security bounds. Are the concrete bounds as good as for the dedicated constructions?
Yes. So in the paper, we give all the security bounds, and they are comparable to the other existing transforms. So it's not like that they have less security. For example, for chassis concretely, we show that the security bound is closely related to the AS/GCM SIV security bound when instantiated when chassis is instantiated with AS counter mode. The security is there.
Yes, so my question is, have you considered the most basic side channel considerations as follows? For example, in some of your schemes, the key is used twice, and some of them the key is used just once in a hash, and it would be easier to protect. And if you hash a key, maybe it enters some expansion inside the hash function, which makes it more leaky. So basically, have you tried to see if maybe you need more schemes which are more resilient to side channels?
Can you repeat the question, maybe rephrase it a bit, so I'm not sure I got it?
Yes, so the question is, have you considered the most basic side channel considerations, such as the use of the key and the leakage of the key? So for example, if you put the key in a hash, maybe this key is expanded a lot and it's going to leak a lot, and therefore the protection of the key could be the first consideration to design your schemes.
No, we did not take that into consideration at all, so yeah.
Anything else?
Thanks.
So actually I have questions. So in what is the overhead of the length of the ciphertext? So you add a tag, but sometimes you add a tag on a ciphertext which already has a tag.
Yeah, exactly. So in the transforms that use the AE, the overhead is 2 n bits. So we have the n bits, let's say, that come from the AE, and then we have this additional n bits from the committing tag. The expansion is optimal for ETH and chassis because one can use the encryption scheme E, so there's no ciphertext expansion there. But regarding the other ones, we say that in the paper, so we did not aim to optimize that. The aim was more simple, understandable, easy to implement transforms. But you're correct, yeah.
Anything else? Okay, so let's thank the speaker again. So that's it for the session. So we have a coffee break now, and we will restart in